In this lesson, we're going to look at graphing data. And what we're going to concentrate on is creating tables of values and graphs, including scatter plots with lines of best fit, identifying and describing linear trends, determining whether a relationship is linear or nonlinear, and solving problems involving linear trends and relationships. The outcomes we're going to cover are creating with or without technology, a graph to represent a given or collected data set. Mine will be done using technology to make it look nice, but you can certainly do it by hand. Solve a contextual problem that requires interpolation or extrapolation of information. Sort a set of scatter plots according to the trends represented, whether they're linear, nonlinear, or if there's no trend at all. Match given contexts with their corresponding graphs and explain the reasoning. Identify and describe the characteristics of a linear relation represented in a graph, a table of values, or a number pattern. Sort a set of graphs, tables of values, and/or number patterns into linear and nonlinear relations. And finally, explain why the points should or should not be connected on the graph for a context. So we're going to start off explaining what a scatter plot is exactly. A scatter plot, this is going back from our last video, is a graph of plotted points that shows a relationship between two data sets. For example, in this graph we see below, each dot represents one person's height versus their shoe size. Okay, when we have a scatter plot, we often see a trend in the data, and when we see a trend, we can add a line of best fit. And a line of best fit is a straight line that represents a trend in a scatter plot that follows a linear pattern. For example, the growth of a plant over a number of weeks is a roughly linear relationship, the height of the plant over those few weeks. So we're going to start with an example here. To observe growth or behavior patterns, scientists measure and tag birds and other animals. Mario measures the height and wingspan of 12 geese. He wonders if there is a trend in the relationship between the two variables that will allow him to make a reasonable prediction of the wingspan when he knows the height. So we have a table here that shows the height and corresponding wingspan of 12 geese. So we want to describe how to set up the axes of a graph to display the data. Explain why you have chosen this approach. I've included the table here again, so we have it as a quick reference. The height in this case is going to be our independent variable. This is along the horizontal axis. The independent variable is always graphed along the horizontal axis. The minimum value in the table for the height of the geese is 77 centimeters. The maximum value is 106 centimeters. So we want to make sure that when we graph our data, that our axis contains all the possible values that we have here. So we have a minimum of 77, a maximum of 106. So if we start our graph, say, at 70 centimeters, and we go up by 5 centimeter increments to 110 centimeters, this will cover all the heights that we have available to us for this measurement. The wingspan then would be the dependent variable. The wingspan of the bird is dependent on the height. So the minimum value in the wingspan is 129 centimeters, and we have a maximum value of 176 centimeters. So we can start our axis at 120 centimeters, increasing it by 5 units again. That's the choice I've chosen, until 180 centimeters. And this will also cover all possible values for the wingspan. We're going to now create a scatter plot of the data. And we're going to determine what is the pattern we see in the points. Now, I used Excel to create my graph. So this is the table that I created in Excel. If you don't have Excel on your computer, You can download a free program called OpenOffice, and it's very similar to Microsoft Office, but it's a free program. Or you can use Google Docs as well. OpenOffice Calc is the spreadsheet program, and it's, like I said, it's good because it's a free program. So when I set up my data, I get this graph. And we can see that our scale for our height goes from 70 centimeters up to 110 centimeters, and we're increasing our increments by 5 each time. And our wingspan, we have between 120 centimeters and 180 centimeters with 5 centimeter increments as well. So we want to describe the trend in the relationship between the two variables. Is it a positive trend, a negative trend, or is there no trend at all? A positive trend is one where as the independent variable increases in value, so does the dependent variable. A negative trend would be where as the independent variable increases in value, the dependent variable decreases in value. And there is no trend when as you increase your value of your independent variable, you don't see any discernible relationship with the dependent variable. So what kind of a relationship do we see here? As our independent variable, the height of the bird, is increasing in size, it appears that so does the wingspan. So the general trend in the data here is positive because both the height and the wingspan seem to be increasing together. And it also appears to be linear. It does seem that these heights and wingspans are somewhat linear. They follow a straight line pattern. Like I said, as the height increases, so does the wingspan. So next we're going to draw a line of best fit. Using technology, it's a simple matter of commanding that the graph do that. If you are graphing by hand, it's you just try to draw your line as best you can so that it fits through the data. We want to describe how well our line represents the trend in the relationship between the variables. So my line of best fit looks like this. Of course, this is using technology. If you don't have technology handy and you graph this by hand, it's certainly acceptable to draw your best guess at where the line of best fit would fall. The idea with the line of best fit is that all of our data points are as close to the line as possible. And in this case, in determining how well the line represents the trend, all of the data points are very close to the line of best fit, and some of them sit on the line of best fit. About half of the data points are above the line, and about half are below. So it's actually a really good representation of the trend we see in the data. We're going to now use the graph we have to predict the wingspan of a goose that is 1 meter tall. First thing you have to recall is that 1 meter is the same thing as 100 centimeters. So if we're looking at our height, we're going to look for where our goose is 100 centimeters tall. So I've drawn a line on the 100 centimeter mark, or as close as I could get. And here it is. So we have the 100 centimeter mark signified here on our graph. What I'm looking for is where my line of best fit would cross the 100 centimeter mark. And where we see that, we're going to now extend the line towards our vertical axis, our dependent variable, the wingspan, which you see here. Now you can see that my line is a little bit above where it should be. It's due to the program that I used. So our wingspan for our bird is going to be somewhere between about 166, 167 centimeters. It's above 165 for sure, and it's below 170, but it should be a little bit closer to the 165 centimeter line. So the wingspan of a bird that's 1 meter high should be about 166 or 167 centimeters based on the relationship we're seeing within our data here. Okay, so we did see a line of best fit drawn through our data. We did see a linear relationship. A linear relationship is a direct relationship between the y-coordinate and the x-coordinate. And all the points on a graph of a linear relationship lie along the straight line. A non-linear relationship is one where there is no direct relationship between the y-coordinate and the x-coordinate. The points on a graph of a non-linear relationship do not lie along a straight line. They may approximate it, but they're not going to be exact. So we're going to compare linear and nonlinear relationships. When Rye was 13 years old, his parents invested $10,000 for 5 years to help pay for his post-secondary education. They had the choice of a simple interest account that pays 3% annually, or a compound interest account that also pays 3% annually. Rye is now 18 and plans to go to college to take a 2-year chef program. We want to create a table of values for each investment, and we're going to round all our values to the nearest dollar. And when we do that, we're going to try to make some sense of any pattern in each column of the simple interest investment. And then we're also going to see how that compares to the number of patterns in the compound interest investment. So the important thing with simple interest is that the interest is added only to the principal amount. The principal amount being the initial amount that's invested in your investment. So if we invest initially $10,000, 3% of $10,000 is $300. That means that every year, $300 is going to be added to our account. In compound interest, it's a little different. The interest is added to the amount in the account at the time. So as more money is added to the account, the amount of interest that's paid out is going to be a little bit more. So the amount added actually changes each year. So here we have our two tables of values. In the simple interest, we see at time 0, the first year, when we initially invest the money, we have $10,000 in the bank account. After 1 year, $300 has been added to the bank account, so we're up to $10,300. After 2 years, another $300 is added, so we're up to $10,600. Another year later, we have another $300 added, so it's $10,900. After 4 years, another $300 is added, we're up to $11,200. After 5 years, once again, $300 is added, so we're up to $11,500. So after 5 years of investment, the value of our investment has grown from $10,000 up to $11,500. In the compound interest, we initially invest $10,000, just like we did with the simple interest. After 1 year, we add 3% to the $10,000, which is $300. Now we're up to $10,300. In year 2, we're adding 3% to the amount in the investment at the time, which is $10,300, not $10,000. So 3% of $10,300 is $309. So now, after 2 years, we have $10,609 in our account. In year 3, we're adding 3% to the amount that we have in the investment at that time, which is $10,609. 3% of $10,609 is $318. So now we have, after 3 years, $10,927 in our account. After 4 years, we're adding 3% to the $10,927, which is $328. So after 4 years, we now have $11,255. And in year 5, we're adding 3% to the amount in our account after 4 years, which is $11,255. And 3% of $11,255 is $338, which leaves us with $11,593 in our account after 5 years. So using compound interest, over 5 years, our investment has grown from $10,000 to $11,593. So notice that the amount added each year when compounding interest does change. So we're now going to graph each set of data from part A in a scatter plot. And once again, I did this using Excel. And we see our two graphs here. There's not much difference between them, as we can see here. And the numbers are a little different, but not by a whole lot. But you may notice that in year 5, our last dot is a little higher in this compound interest graph than it is in the simple interest graph. And we saw that in our table that after 5 years we had a little bit more money in our account. We're going to graph each set of data from Part A in a scatter plot. And I have borrowed the pictures from the book because it better illustrates it than what Excel could. But when we see the simple interest investment, the line of best fit actually goes right through every single data point. Whereas you should be able to notice here that with the compound interest investment, each data point seems to be getting a little bit more further away from our line of best fit. It's a little bit higher every time and moving a little bit further away from our line of best fit. So what do we notice about the pattern? Well, it's exactly as I said. For the simple interest, there is a positive linear trend. We did see that the line seemed to go right through every single line. All the points lie directly on that line of best fit. For the compound interest, it is approximately linear. It did look pretty close to linear, but it's not perfectly linear as it was in simple interest. We did see that the dots appear to start to veer off our line of best fit. So it can be considered nonlinear as a result. So how does each graph relate to its table of values? The simple interest numbers in the graph increase by the same amount each year. So does the numbers in the table. Every year, $300 was added. It was consistent. It was $300 every single year. This is the reason for our straight line. We had a constant increase of $300 every year. Comparing that to our compound interest, the compound interest numbers in the graph increase again by a slightly larger amount each time, just like with our table. This is why the points are not exactly on the straight line. Rye's parents chose the compound interest account. Did they choose the right investment, do you think? Explain your answer. Well, the amount of money in the investment is increasing more rapidly in the compound interest plan than in the simple interest plan. So they did make the right choice. If they were able to let the investment grow for a few more years, the gap between the amount of interest they earned in the simple interest account and the amount they'd earn in the compound interest account would grow even greater. So last question here, should the data points be connected in the graphs? And explain your answer. Well, the answer to this is that no, they shouldn't. And the reason is because the interest is added only once every year. So from day 1 to day 364 in that year, the amount of money in the account stays exactly the same. It's on the 365th day or 365 days later that the amount of money in the account will change. It only changes once a year. And we did see lines connecting or attempting to connect the data, but we only did that to visualize the trend. It's not actually necessary to be there, and in fact it shouldn't be in general. Whenever we have data that changes only at certain times, we will not connect the data. So to summarize, we can graph a scatter plot of the data in a table of values to view the trend in the data. And we can determine if the trend is linear or nonlinear, or if there is no trend at all as well. Using technology, or our best guess, if we're doing this by hand, we can create a line of best fit to show how well a scatter plot fits or does not fit a linear trend. A linear trend can be positive, where the independent and dependent variables both increase in value. It can be negative, where the dependent variable decreases when the independent variable increases. Or there could be no trend, where there's no discernible relationship between the independent and dependent variables. the dots appear to be random on your scatter plot. And often it does not make sense in the context of the problem, much like in the last one we did, to connect the data with a line. Okay, but again, we did it for analysis purposes, so it may be done when you're trying to come up with a line of best fit.